Sir, good evening, sir. Nayak, sir, good evening, sir. Sir, good evening.
Yes, good evening.
Good evening, sir. Good evening, sir. Sir, good
So
evening.
hope everything is ready, right? I'm just ready being. My voice is clearly audible, right?
Yes, sir. Yes, sir. Yes, sir. Audible.
Okay. So only
Exactly.
thing is voice is important. If I'm not visible properly, that's okay to me, no problem.
Yes, sir.
But the voice will be clear. Okay.
Yes, sir. Yes, sir.
If anywhere it is being stuck, please let me know.
Yes, sir. Yes,
So
sir.
I'll restart again. No problem.
Yes, sir. Yes, sir. Yes, sir. Exactly 6 o'clock with your
Yeah.
permission.
Okay. No issue. Okay.
Yes, sir. Thank you. Sir. %, scientists Stanford University of California. Dear participants, my voice is audible to everyone.
Yes, sir. Audible, sir.
Yeah. Thank you, sir. Thank you, sir. Pencilai, sir.
Welcome, sir.
Yes, sir. Dear participants, very good evening to one and all. It's my pleasure and a great honor to welcoming our beloved professor and my guide, my mentor, and everything for my education and academics for accepting our request for taking one important session on ATAL sponsored 1 week faculty development program on quantum cryptography enabled autonomous underwater vehicles. Sir, we are very much grateful for accepting as a resource person in this ATAL FDP program, sir. Nayak, sir. Very good evening, sir, and very warm welcome on this ATAL Faculty Development Program, sir. On behalf of the Department of Computer Science and Engineering in NBK or IST, we are very much proud and we will feel great, sir, for taking session on our faculty development program. Ma Ritika, kindly introduce our beloved professor, my mentor, my guide, Dr. Janmenjoy Nayak, sir. Sir, thank you, sir. Thank you for giving your valuable time for this session. Thank you, sir.
Welcome, sir. It's my pleasure to have this session.
Sir, thank you, sir. Ma Ritika.
Yes.
Ma.
Good evening, everyone. It's an esteemed pleasure to introduce the luminary of today's first session, Dr. Janmenjoy Nayak, sir, Assistant Professor at MSCB University, Odisha, a trailblazer in the realm of data mining, applied artificial intelligence, and IoT security. Dr. Nayak, sir, brings with him a wealth of knowledge and expertise. With an extraordinary record of over 210 publications, Dr. Nayak, sir, has cemented his position as a leading researcher in his field. Sir's exceptional contributions have earned him recognition among the top 2% scientists globally by Stanford University, a testament to his academic prowess. As a senior IEEE member, he continues to inspire and influence the next generation of researchers. Dr. Nayak sir's academic journey is a testament to his dedication and excellence. A gold medalist in both his Master of Science, Computer Science and MTech in Computer Science. Sir has received numerous accolades, including the prestigious Best Researcher Award from Jawaharlal Nehru Technological University and the Inspire Fellowship from the Ministry of Science and Technology, Government of India. With an impressive 6,362 citations on Google Scholar, Dr. Nayak sir's work has had a profound impact on the academic community. Let's extend a warm welcome to Dr. Nayak sir. We are very honored to have you with us today, sir. We welcome you, sir.
Thank you, Maritika.
Yes, sir.
Sir, with your permission, we are going to hand over this session, sir.
Thank you.
Thank you for accepting our request, sir. Thank you, sir.
It's always my pleasure.
Sir.
And I think you have taken first 4 minutes of mine. I'm so sorry for that. Okay, so exactly the session has to start at 6 o'clock. So good evening, all the participants, and it's always a great pleasure to be associated with Dr. Chandrakant, who is well known to me from no long time. And this topic, quantum computing, is one of the emerging topic, we can say, but it is excelling very good in current days. So it's always a good topic to be discussed, and I feel last few days onwards, I think already 5 or 6 days has been completed. Many of the speaker has already been covered most of the concepts, and I feel like it will be very easy at my side to complete my part, because what I feel from the beginning, all the introduction and rest of the things have been covered. Okay, so first let me allow to share my screen, please. Then I'll start my talk. So if I'm sharing this, is it visible at your end?
Yes, sir.
Yes, sir. Visible, sir.
Sir.
Okay. Now I have done full screen. Is it full screen at your end?
Yes, sir. Yes, sir.
Okay. Now I'm moving. Is it moving?
Yes, sir. Moving. Sir.
Okay. Okay, fine. That's great. So let us talk about simple means what the other things we want to talk. We will talk after the talk. And first, let us talk about for which we are here. So I believe all the participants, they are pretty active during the session, and in 1.5 hours, I'll try to conceptualize most of the important topics where not only sole quantum computing will help you to go forward, rather than uh, most of the participants who are participating, I strongly believe they are actively working in either machine learning or deep learning, because these days it's a common scenario to work with any of the algorithm of machine learning and deep learning. And that's the reason, being I can say a normal researcher, I feel let us talk little about how we can integrate machine learning with quantum, and it will also purposefully solve your problem. And I'll share a very good interesting one slide for all of you, like related to your FDP title. The title is very interesting. I have gone through it, and I can say little in a packed schedule how far I have gone through little time to search your title, the FDP title, and I have done a very thorough investigation on the title of the FDP and how the organizers have chosen the title. It's really impressive, and I'll tell a few good things to all of you. Okay, possibly all other speaker may not cover that. Okay. So quickly, let us come to the topic. It's quantum machine learning, and what are the emerging paradigms? We are going to cover it. Okay. So these are my contents. Before let us segregate my talk into 1 hour and one last half hour, like that. Because 1 hour I'm going to talk about. In that 1 hour, please split into 10 minutes. So each content what I have shared, I will give a good deliberations on AI, ML, big data, and DL. Then exactly where quantum computing is needed, or somewhere at some point of time forcefully we are trying to just integrate quantum computing as all are talking about it. Like these days, even my students, they normally used to tell, sir, it's an era of deep learning, right? So let us little not talk about classical machine learning algorithms. So those who really works, it's a very good thing to know that still now there are few problems in the real world or engineering where a simple KNN method has not been applied yet. Those problem areas we need to understand. So KNN classifier or K nearest neighborhood no basic classification algorithm or K means clustering algorithm are not at all traditional or classical algorithms. We need to understand those. So what I believe, if something is emerging, that doesn't mean the classical parts have been completely outraged. No, not like that. We need to understand with all those classical computing methods, what we can integrate with the present modern techniques, we can say. Okay. So I'll talk about AI, ML, as well as big data, the deep learning, and where the challenges are actually relying. Then we will move towards the quantum computing, the principles of quantum computing, as well as the components and few use cases. Then directly we will come across where machine learning and deep learning are actually needed in quantum, so that it will help us, or it will help all those machine learning and deep learning based researchers to go forward. Okay. So technically, let us start our talk. So it's all about, it's AI, and I feel I have nothing more to say about it because it's a basic paradigm where we know it very well. And if we will talk about it, most of the time, like we are assisting with the rise of AI, but um, today all such problem is not there where AI is not applicable. First thing, okay, most of the cases we will find AI and its applications. If you will talk about, starting from the virtual assistant or any self-driving car, which is again a previous no very well-known applications, I can say. But is it going to change our habit? Okay, that is one of the good thing we need to understand. Or simply it is not going to give us something else, like where and how we are not facing those challenges where AI should not work, or AI is not needed. Can anyone say where AI is not needed? I don't think. I think some problem in the, sorry, where this my slide are visible or something else is visible to you?
No, sir. Slide is visible, sir. Artificial intelligence slide, sir.
Okay, okay,
Two and a half minutes, 3 points.
wait. At my end, what happened? Something, this Zoom came. Wait. Okay. Uh, I'm sharing it again. Please wait.
Oh,
Problem is this Zoom came in front of me. It should not come like that. Wait. Sorry. Okay. Yeah. Now my slide is there. or
Visible, sir?
something else is?
No, sir. Slide will
My
take.
slide is there?
Yes, sir. Is here. See.
Okay, wait.
Having 3 points in 3 diagrams.
Please wait. Yes. Yes. Yeah. I think it's visible now, right?
Yes, sir.
Yeah, there are few technical issues at Zoom, and I guess it came in front of my screen. Okay, sorry. So, what the thought is, many of the people they used to talk like whether it's a technology or where the AI has been used or why it is being used. Okay, but the fact is we are not able to get exactly how the AI is creating no different kind of machines to perform various kind of engineering problems. Oh, and mostly it is giving us a lot of solutions, but still now what being a core researcher of AI, we strongly believe still AI is a fuzzy concept because we used to tell yes it is good, and most of the unknown people they used to tell no, AI is making lazy. And last week only this TCS and Wipro kind of companies have laid down some of few of their what employees and all. In that case again few people started talking AI is taking all the jobs. So there are myths, I can say. Most of the things we are coming with the myths, okay, but we need to understand how AI is actually making stronger, and it will really helpful to most of the people in the next generation, I can say. Okay, so it's not all about all the time AI is taking all the jobs. No, AI is not at all responsible for taking anyone's job. Please keep mind in that, because it is one of those concepts where if number of AI expert will increase in the market, definitely the latency of jobs will increase in that aspect too. Okay, so AI neither making anyone's idea or it is taking anyone's job or something like that. So it is just an actor or architect where it makes some decisions, right? Like whether it is ethical without being AI or whether it is being conscious or moral being. It depends now how you are going to take about the boundaries of AI and where you are going to set the limit of AI. Okay, now quickly please come across there are 3 stages of AI. One is narrow, one is general, one is super. Okay, so basically how we dealt with narrow and general, in that way we are trying to cope up with super AI, but the problem is we are thinking to any area we can apply super AI, but it's practically little impossible. But again the problem is whether the number of areas which are being already covered by AI, are they outperform or equal to the humans? That's a black box. We need to understand that concept too. Okay, so basically general AI means able to autonomously solve the problem, and super AI where you are going to talk about super AI, it's a basic concept of problem solving approach as well as outperform human in all the areas. So that's the basic difference if you will come across where super AI actually works. Okay, uh, this is a very interesting slide. If you will go through 1940 to 2020, you can see the huge gap of generation. Like since 1940, you come across 2020. And please look into the fact, since the development of neural network, we came across LLM. Now all are talking about LLM, right? In 2025 almost. So ChatGPT, this number of all no, Gemini kind of thing has been developed. But at the same time, how many of you know it almost took 80 plus years to become the most hot sensation in the market? That means from those era to this era, or I can say a decade, something like 10 or 20 decades, it is how much it is difficult to get those insightful developments starting from a basic normal maculopete neuron or a neural network. Okay, so that's the progress of AI in current days we are seeing, and where this number of different computing methods coming to the market, those we are trying to adopt. But at the same time, we are having some of the limitations as well as few problem specific domains where some problems can be applied, some other problems may not be applied. Okay. So the basic part or the most interesting part of AI, if we will talk in current days, is machine learning, right? And I hope most of the participants in this session are working on the machine learning. Okay. So let us take a quick review. Okay, it will take some time, but let us take just few seconds. Can you please use your chat box and write something who has used what is the latest or last algorithm of machine learning, so that we will come to know how much the participants are active also in the session, right? Make it quick, please. So I'll jump to my content. All the participants, please use your chat box and let me know how many of you has used machine learning algorithm recently, any day, any algorithm you have used or you know it. Okay. So we got a few responses. I hope those are active and remaining people somewhere they are not active. It's okay. So let us talk about few things which we can know exactly know about how machine learning works. Okay, we know it, but we need to understand like how far the machine learning exactly gives you the system to ability or automatically learn. That means machine basically used to take the past data where we used to also no claim that we can learn many things from the experiences. So based on again the human concept, this machine learning has been evolved and it just focuses on the development of computer programs that exactly gives you access to the data as well as used to the large content. So this autonomous kind of mode of learning is very important, and there itself we used to consider most of the part are useful, and slowly machine learning has taken over all the classical computing methods. Okay, now why my screen is not moving? My screen is not moving. What happened? Hello, am I audible?
You're audible, sir.
Okay, I think the system is slow. Yeah, my screen now moved. It was not moving actually. Did you get the slide of the flowchart of machine learning?
Yes, sir.
Yeah, okay. So this is a basic process of machine learning where we need to prepare the data and we need to brain and build the models and deploy and predict. So all the researchers are very much happy with this process because always everybody feels, especially the researchers of cloud computing and no security aspect, those researchers or IoT based security people, what they feel is machine learning research is pretty easy because it is a data based research. Most of the people, they used to consider data, they used to prepare the data, and they used to train the model accordingly, then they will get some result. How they are getting the result, very few people know. And as I already believe, when Python came to market, again everybody became little more lazier because Python has all the inbuilt code, and Python and GitHub everybody is using in that way, and everybody is happy because they are getting some outputs and some colorful graphs without knowing exactly what is happening at the back, because that part is very important, right? So that is one of those drawbacks we can consider. Now Let us talk about little on the data growth. Now, why we are actually moving towards quantum computing? The basic reason in that is this, where most of the people, they are not talking about the data growth, because last 1 decade and previous decade has seen an ultimatum growth in the data due to various social media accounts. First thing. Second, we can consider video, audio, or any textual data. But any one day, it is not at all stopping. The growth is increasing in an exponential way, we can say. So the problem is, means almost all the problem lies here, where most of the system, what we are talking, is related to the data. Now, can you please correlate the structured or unstructured data? In the graph, you can see the amount of unstructured data is huge, and the amount of structured data is very less as compared to that. And approximately from a review I have taken, if you will go across the 78 yottabyte, and what is the yottabyte? You can see, you can count the zeros after one. Those many number of bytes. Okay. So the fact is, it's a huge concern for all the computer science people as well as the computer science researchers. And currently, both AI/ML and data science are with maintenance of that gap of data. That means how to handle data. And if any of you is really able to handle a proper data or a unstructured data to make it a convenient structured data, then obviously your task is a huge task and it has been successful. Okay. Now, what is the solution of it? And with that, we again come across a new term that's called big data. So I have dedicated only one slide to the big data. What is that again? So it is just a 1 terabyte we used to consider as a official number. But normally, if you are having more than 1 TB or 2 TB kind of data, you can find any complex number in that. So we consider it as a big data. Okay. Now, the fact is, uh, we are having the data set, we are having the generation of data, whether it is, you can consider anything, you can consider any live running data of IRCTC or any of airlines kind of thing. You can consider anything, but the data is not stopping, rather it is increasing. So the term is simple term, big data. We used to consider how to handle big data. Now, in the market, these are the three types of data you will find. The first kind of data is structured, second one semi-structured, third one unstructured. As I told you, most of the unstructured data you will find in the real life scenario, and very few structured data you will find, for which you can do some experiments with them. Okay. But most of the time, you will find the unstructured data in the form of social media and remaining all kind of database, online database. Now, what is our task? Being a computer science researcher or computer science man, your task is a very simple thing, that's called taking all the unstructured to structure. Just make it unstructured to structure. And that's all about computing or proper computing. Okay. So modern computing technology concerns both hardware as well as software, because we only cannot say Python or MATLAB's kind of software are really enough to handle everything. But the fact is, we need some specialized hardware to precisely handle all those softwares for smoother experimentation of all the methods. Now, the fact is, how far we are able to do or develop that in the current scenario of modern technology. Okay. So, this is the basic thing. I hope all of you know, like how you are going to choose a basic machine learning algorithm. What exactly the parameter you are going to consider. There are much concept, I can say. The concept is, first you can know what kind of problem you are considering. Second, what kind of algorithm you are considering, right? Size of the training data, always it matters, because If you are a proper researcher, you will definitely see what should be the size of the data and what is the model you are considering. If for the size of the data, the model is accurate or not, that you need to have a proper balance in between bias as well as the variance. Okay. At the same time, whether you are able to measure the effectiveness of your model or not based on the total proportion. Next, the speed or training time. That means how far your model is taking a proper time or the gap of time between all the algorithm, or the training time is really close or tied to accuracy. That means your model is really accurate or not within a limited time frame, or the training time is not too much high. And how many number of parameters you need to adjust, that comes under number of parameters as well as the number of features. As we know, features are basically the quantifiable variable which actually help us to analyze the model. Okay, so there are multiple criteria to choose a basic machine learning algorithm. At the same time, if you are going to talk about few limitations, as I told you from the beginning, there are few limitations of ML where we need to think of it. Like, always please remember, while you are going to deliver the limitations of machine learning, you have to consider how it is a black box, because uh, due to inbuilt codes, due to few training, by default training procedure, I can say, or ultimate kind of training from the first epoch to the last epoch, the complete process of machine learning becomes a black box. That means the user who is using, they are completely unaware about what exactly they want to do, but they are getting some output and they are happy with that output. If really it is somewhere some kind of performance parameter they are considering, it's called accuracy. Okay, so if you are going to talk, you are having data dependency as well as the bias and discrimination. Always, no, you have to look after the training data, means how much the training data contains bias, as well as the ML model can learn or amplify those biases, leading to the unfair or discriminatory outcomes. That means how your input is giving, that much output you can expect from your model, a basic simple line. But at the same time, what about the cost? Very few research paper talks about cost, but most of them are relied on the kind of performance parameter based on accuracy. But at the same time, if you are going to talk about the computational cost, you are considering large data set, right? As well as the complex architecture. At the same time, ML model can be computationally expensive. It has been proved in simultaneous number of research papers. Okay, it's a fact that we need to come across through number of specialized hardware as well as expertise, both, because always there is a trade-off between the model accuracy as well as how you are going to deal with the hardware. Okay, and I hope I should not say much about the overfitting and underfitting issues of any model, because when normally a model learns the training data too well, and including it doesn't understand whether it contains noise or performs poorly on the new data or not. But at the same time, it fast results with the overfitting. But if you are talking about underfitting, it really occurs when a normal model used to give you the failure of capturing underlying patterns in a trained net, because we cannot say exactly how no how much or how far the data is suitable for my model, or the model is not really understanding what kind of data you are going to give. So these both issues are very general issues of most of the machine learning problem, right? But still, we have done a complex, very good problem solving approaches to machine learning, and there are huge, or I can say bulk amount of research is exactly existing in the current no literature. So if you are going to talk about generalization again, the model always they are not fit to all the unseen data. That means how far you have trained the data, the model will behave accordingly. If little your data or the size or shape or behavior of the data little changes, then the model may not exactly generalize the concept. Okay. Now, suddenly people have jumped from machine learning to deep learning, the next level learning, right? People used to feel deep learning means complex network. Deep learning means more deeper structure. as well as how many layer I will include. The depth of the network will always allow me to learn the complex pattern. That's true, some up to some extent, but if you will compare in between the machine learning and the advances of machine learning in the form of deep learning, it simply no I can say differentiate in the term of automatically extracting the feature, nothing else. Okay, where the trained features are different, and how you are going to take with number of applications with automatically giving you the recognition or extracting the number of features what you want. That is possible with number of layers or number of nodes what you are going to increase. But again, here there are some problems. We need to understand that also, because it's not something which is very different from machine learning, but up to some extent it is useful for us to give us some good solutions, right? At the same time, the data quality and bias is a very important factor in the deep learning. We need to understand that. And while we are going to talk about some of the expensive computational tools or some good models, expensive models, which actually require GPUs and TPUs, in that again, there is a concern towards the complexity, right? And I hope you people know all about handling unstructured data is also again a problem with deep learning, as well as how much computationally intensive and require significant memory to make them difficult to scale to a very large data set, because always we cannot have that flexibility towards the scalable deep learning architecture. So what we have covered is there are few limitations where we are leaving machine learning. Again, we are jumping to deep learning. Again, the problem is where deep learning again lies in some of the papers, and a few good researchers have talked much about the complexity and the cost of deep learning models, right? So as I told you, now please you correlate. You might think our topic is quantum computing. Then why SAR is covering machine learning and deep learning? Now, from this slide onwards, you will come across directly where the quantum computing. And please correlate how these deep learning, the limitations, machine learning and the limitations, as well as one slide which I have dedicated to big data, how they all are correlated or interrelated, so that you can jump to quantum computing with a reason. We should not jump to quantum computing without having a proper reason, right? It is not just another computing technique. It is one of those, we can say, advanced computing, or we can say one of the revolutionary approach. So where exactly the limitations we have found over here, let us talk about the much more talked topic on the computational complexity, which relates both the space as well as the cost. So that where we starts with quantum computing, right? So it is one of those concept where you are exactly relating to the computation at a higher level. And basically quantum computing is nothing but it's just a concept based on principles of quantum physics. Normally we used to cover in the terms of graduation, or I can say few small concepts in +2 2. Quantum physics is a very important topic, as well as no, it always talks about much faster, like how we are going to take quantum computing starting from the classical computing. Now, as a physicist, it is very easy to understand quantum computing, but as a computer scientist, I feel it may be little difficult to understand. But again, it's not that internal mathematical mechanism which actually a physicist require. We too require that, but we need to understand how it is correlating with a very small concept like atoms as well as the photons, like to exactly process which are little difficult at the classical computer age. If you are going to talk about quantum computing as well as classical computing, there are basic things you will find, like what quantum computing deal. First thing, you will find QC that means quantum computing, you will find with the nature of no complete computing methodology with quantum level. That means, what is a quantum? It's nothing but a small or minimum amount of a physical entity which can be considered in terms of computing. Got it? But the fact is, the basic idea is to operate the computer on very extremely short pulses of light. That means we know it can speed up the operation of computer how many times? At least 1 lakh times, which we need because our volume of data is so high, and we need little powerful computing methodology where we can deal the problems with some fraction of seconds or some minutes, right? So it's a fact where the data in such computer are not stored directly, rather they're going to convert into quantum bits. Please understand, there are two good concepts. One is classical computing, one is quantum computing. In classical computing, basically your classical computer, what you have considered is a laptop or phone, where it normally uses the bit of either 0 or 1. As we know, it's a binary bit. But if we are going to talk about quantum computing, the one small new concept is there, which is known as qubit. What is qubit? Qubit, in the sense, it can be both 0 and 1 at the same time. Now, why it is at the same time? That we need to understand, because it require a proper exact property of physics that's called superposition, right? And the guys who are very clear about the superposition, and I hope other speakers might have covered what is superposition. So it exactly tells us at the same time we can have both the entity called 0 and 1. Now that makes it very strong. Now, if little you will go to the evolution of quantum computing, it starts, no, exactly, it takes the concept little bit. It takes the concept about classical computing, where we used to talk about the binary system, as I told you, either 0 or 1. Then you will go across the transistor. Then please see the serial numbers. Number 2 is what? Quantum mechanics, where you will talk about superposition and entanglement, qubit, quantum gates, IBM Q system 1. There are a number of other processors, but the future applications of quantum computing is very high. And mostly for the cryptography applications, that means which is relating to little error correction or detection and the security. That part is being nicely covered with quantum computing, where people used to think in a very good concept, like how we can use it with most of the applications in the real life. At the same time, how far, apart from cryptography, some other good engineering problems like medical or healthcare or some drug discovery or any of good text processing or no social media content analysis purpose, we can use it. So we will talk a number of things in upcoming slides. Okay. Now, let me tell you what is a qubit. So if you are going to talk about quantum computing, as I told you, it simply gives you some good behavior studies on photons, electrons. And for what exactly they do? A good performing calculations. That means on a large scale information processing, the basic quantum computing exactly is helpful to give you some good atomic particles. Now, at the same time, whether the advantage you are going to get and what kind of features you are going to get. Now, here in quantum computing, your feature will be quantum features. Okay. That means the quantum features in terms of either entanglement or superposition. Now, if you are going to talk about superposition, as I told you, the qubit has to exist in multiple states simultaneously, means both 0 and 1. That means it exactly gives the quantum computers to explore many possible solutions at one time. That means we cannot say at one time only one computation is going to perform. A very simple thing. Now, if you will go and talk about entanglement, what is that? Now, where the qubits can become linked so that the one state can affect the other. That means when, if they are very far also, it is actually helpful for correlating the classical normal computing method. That means in classical computing, you cannot do such thing at the same effect where the qubits or such kind of good uh, ratio or good distance, you can easily find it out. But at the same time, what is the capability of this? If you are going to talk the capabilities which exactly gives you the quantum computer in the terms of both the time and cost. As I told you, there are two major things or major reason we are moving towards the era of quantum computing. Now, what is a qubit? As I told you, it's qubit means it's quantum bits, okay, in a short form. Now, they are represented as quantum particles. Now, the manipulation of qubit by control devices is mainly the core of a quantum computer processing. That means the value of classical bit can be 0 or on, that means on or off, or 1 or 0, where the qubit is completely based on the law of quantum mechanics. That means it has to be placed on a superposition of states. Okay. Now, what are the types of qubits? I don't know whether other speakers have covered the types of qubits, because when you are going to deal with the hardware concepts of quantum computing, you need to understand which kind of qubit you are going to consider. And basically, these are the good kind of qubit. For the first one, you can say superconducting. Second one, the trapped ion. Third one, the quantum dots. Fourth one, the photons. Okay. Now, when you are going to talk about 100 qubits, the range is almost astronomical, because when the qubits are combined together, their superposition can grow exponentially. And 2 qubits can be in a superposition of the 4 possible 2-bit string. And if 3 qubits you are going to take on the superposition, then you will get 8 possible 3-bit strings. It's a very simple formula. I hope you can understand it. At the same time, how qubit behaves like in a classical computer, here the qubit will behave like a bit, and it stores either a 0 or 1, but it can also be weighted combination of both the 0 and 1 at the same time. Now, where and how we actually needed the types of qubit, and what are the different applications and strength of all these qubits. When you are going to talk about supercomputing qubit, now they are completely made from the superconducting materials. And if you want to work on very extremely low temperature, then these qubits are very helpful. Okay. But if you are going to talk about trapped ion qubits, now trapped ion qubits are those ion particles where you can also be used for the qubit and for the long coherence times. That means their fidelity measurement is little higher, but little slower as compared to the superconducting qubits. But apart from all this, the quantum dots are very famous, because people like since IBM has started the quantum mission, most of the places you might have seen the quantum dots. That means they are nothing but some small semiconductor, you can say, like they capture a basic single electron, as well as they use it as a qubit. That means that single electron behaves like a qubit, which actually offers you some scalable information. At the same time, if you are going to talk about photons, they're individual light particles. They have nothing to do with some kind of distance or long time coherence time. At the same time, they can make the qubits and send the quantum information across long distances. So these are the 4 types of qubits where most of the quantum computers are really adopting for the next era. Now, as I told you, these 2 concepts are very, very important in terms of quantum computing. And as we are going to understand the machine learning involved with quantum computing, how these 2 concepts actually helps us. The first principle is superposition. Second is entanglement. Now, superposition, as I told you already, they are just a group of qubits where it can complex, or it can simply group some complex multidimensional computational spaces. At the same time, if you are having a good ability to correlate the qubit state, then entanglement is helpful. And quantum entanglement occurs when 2 systems link so closely that knowledge about one gives you immediate knowledge about the other. That means how far they are apart, they are staying away, or little they are maintaining the distance. They may not have a proper stability in between the correct linkage. So these quantum processors actually can draw the conclusion about one particle where the other is going to measure it. Okay. Now, people used to discuss these two. Normally, people used to feel the principle of quantum computing when you are going to understand superposition and entanglement is enough to move forward. But fact is, if you are going to talk little good principle in these two forms like decoherence and interference, these are as much important as compared to those two. How? Now, where you are going to talk about the loss in the quantum state, because every time when you are going to apply the principle of quantum mechanics, we may expect there are few losses in the quantum state in the qubit. At the same time, the environmental factor like radiation, which can cause the quantum state of the qubit to collapse. It can be intentionally triggered by measuring a quantum system. But when you are going to require some of the avoiding and minimizing decoherence, then definitely quantum computing helps you. That means a good quantum computer always used to avoid and minimize the decoherence to get a proper output on the basis of your input. At the same time, if you are going to talk about interference, then it is simply an environment of qubits which placed into a state of collective superposition structure. That means it looks like a wave, or you can say some kind of amplitude, but the amplitude are the probabilities of those outcomes which of the measure of the system. That means the waves, either it is going to build on when at the peak of the particular outcome, or it is going to cancel each other when it peaks throughout the interaction. Now the problem is, most of the people, they used to feel how far quantum computing is actually useful. Main concept behind it is the quantum computers can actually theoretically solve certain problems which are really exponentially faster than the classical computers. Mostly we used to call NP hard and those kind of problems. That means computationally sensitive problems where we can find some good solutions. And if you are going to consider the best measuring problem in that category is optimization. We know optimization problems are being always tough to solve, but at the same time you can find some good other applications like cryptography, some good simulations, or the basic data analysis or machine learning kind of problem can be easily solved with it. Let us know more about it. Now, what are the components? If you have the quantum processors, then you are going to talk about QPU, like quantum processing unit, which includes quantum chip, the control electronics, as well as the classical computer hardware. Second part of your component of quantum computing is the control, because most of the computer use the circuit and the capacitors. And when you are going to exactly fire the microwave photons into the qubits, then there is a control to obtain the behavior and get them hold to the change. That means your control must hold when you are going to talk about a proper capacitor or the proper development of good microwave photon. So what about the superconductor? We normally expect our computer has to be very faster, right? And most of them, and in most of the cases, we are not able to get this cold enough kind of feature. Like your desktop computer, mostly people used to complain the fan is not cold enough to work. But if you are going to talk about the superconductor, they are actually helpful, or you can say the quantum processors, which need to be very cold in a hundredth of degree above absolute zero to minimize the noise. I hope you understand why I told you to avoid the decoherence and the minimization of decoherence, because always the quantum states used to revolve into those scenario where they need those cold environment. Now, the ultra low temperature is achieved with the supercooled superfluids with the quantums or quantum bits, where the temperatures exactly works on certain material where it exhibits the important quantum mechanical effect. And if you are going to talk about little software, then 2024, the last year, I hope all of you know or not, IBM introduced the first stable version of this QAS kit, because we used to call since 2016 around quantum computers are coming, or quantum computers will evolve into next level, but the exact software development kit was this quiz kit, no, SDK 1.x. Now, how it became popular, you can find it out like over the night. Some 6 lakh kind of registered user, and some kind of number of institutes have recognized it. So overnight it has that limelight to come across through quantum computing. Okay, now what are the cases? If you're going to talk about, as I told you, the use cases are very huge. That means you are going to talk, you are going to consider in pharmaceuticals, you are going to talk in chemistry or machine learning, or some other applications too, like drug discovery or medical kind of thing. Now, why you can find little more discussions on the few applications. If you are going to talk pharmaceuticals, actually, quantum computers are really helpful to get the behavioral analysis of molecule or the biochemical reactions, which little earlier it was tricky with the classical computer, because we need all the classical machine learning or deep learning based algorithm. What they need is a good pattern. That good pattern itself, no, sometimes it becomes a very complex structure. So those things can be easily handled now with quantum computing. If you are going to talk about chemistry, at the same time, it may impact you in mitigating some of the dangerous or destructive chemical byproducts. And it exactly helps you to improve the catalyst and some better processes for the carbon breakdown wherever it is necessary to combat the climate threatening emissions. So we need some immediate responsive solutions. And for that, quantum computing raises its hands at the first. Okay. Now, let us talk about the most interesting part of it is machine learning. As we know, many of the problems has already been solved with machine learning, but as I told you, the complexity of all those models is always has stood as a challenge, and we need to think of every of all those applications, like how far the machine learning are really helpful, and they are going to take about good tech forwards kind of things with the integration of quantum computing. Now, let us talk about quantum machine learning. Now, why and how it is required? First thing, it is required to integrate, means you need to integrate quantum computing with machine learning just to overcome the limitations of classical computers for large scale data set as well as computationally intensive tasks. I hope this slide elaborates you till now what we have covered. That means why and how machine learning and deep learning are actually coming forward along with the integration of quantum computing to make solve of all those complex problems. So task, as I told you, we are focusing on the speed, we are focusing on the architectures as well as the number of kind of hardware as well as software solutions. Now, there are few quantum hardware solutions which already I discussed, like computing or superconducting qubits, the trapped ions, the photonic qubits, the topological qubits. Now, where you are going to talk about the superconducting qubits, those no, basically the circuits are cooled to nearly absolute zero temperature. Like good companies like Rigetti, Google, and IBM, they are providing those. If you are going to talk about the trapped ions, the ions which held in the electromagnetic field. So the four type of quantum hardware actually in which way they are helpful to take across this machine learning. That integration will help you to go forward for the fast and good efficient training to all the machine learning models. Now, let us come across to combine machine learning as well as quantum computing. And before I'll start to the next slide, let me tell you very frankly, the machine learning researchers who are attending this FDP, please understand, if your area of expertise is machine learning or deep learning, take your own time of another 3 to 4 months to understand the basic quantum computing algorithms as well as the programs. Then you try to integrate, and trust me, your research will go up to next level. The reason is, currently those who are writing some good papers on machine learning or deep learning, they're thinking again the same process. Like if you will pick, I can say mostly 10 to 20 papers out of 100 will talk about the complex architecture or some solutions or some qualitative discussions on the model. Remaining 80 to 90 papers out of 100 will give you the data sets, the results, and few good applications, how they are proved to be solved through machine learning, nothing else. Okay, but few of you might have gone through rejections also by some journals. You may not know why the journal is telling out of scope, why the journal is telling no, this kind of work is the research is very limited kind of word, like very kind of catchy words the journal people used to use. So most of the time, we since I can say 2024, mid of 2024, like that, almost 1 year happened. If you will see, or if you will come across, like I am currently working as no associate editor of many good IEEE and LCBS major journals, where I have come across the same. When most of the articles are coming, I'm screening, or we are pre-screening it. During pre-screening, we are exactly seeing the same, whether the paper is only on the machine learning, the paper is only on the deep learning, the author has taken one data set, tried to solve some problem with some of the performance matrix. Then this was the research of, no, I can say 2010 to 2018, like that. But last 7 8 years research has evolved in a new era, or I can say it is going in a very different directions. And till now, if you are not able to know that, please consider it in a very serious issue. Don't consider taking a data set, apply one machine learning using Python, then get some results, then write some paper and submit it somewhere to some journal or conference to get it published. So that is not going to work out. And if you want, if you may search the research paper related to quantum machine learning in the Google Scholar, you will find very limited paper. That means now there is a perfect time or scope to move forward with the quantum computing, integrating to machine learning. That means what you have learned as a machine learning researcher, that will definitely help you to move forward, right? So these parts I'm taking to my next slide. Am I audible, guys? Everything is silent actually, so I'm not able to know whether everything is reaching to you people or not.
Yeah, sir, you are audible. And
Okay,
yeah.
okay, fine. So things are going fine, right? Okay,
Yes, sir.
good.
Fine.
Okay. So now the question is, some of you might think, like before you will think, I have kept my slide because I know there is a one-way communication during online sessions. It's not an offline session. So when you will think, why to integrate quantum computing with machine learning? As I told you, three major problems we want to solve. First thing, enhance performance with a complex problem. Second, faster algorithm training. Third, the large and high dimensional data set handling. If you will see, these are the three major issues of any machine learning algorithm, right? But if you will consider quantum computers, they can really process very good information, which is exponentially good, other than the classical computer, which actually allow them to solve some complex problems. Coming to training, we know quantum algorithm are dramatically reduce the time because they used to train the machine learning models very quickly, and how much the size of your data set also, it rarely matters to the fitting of the model. That means the model learns very quickly. So actually it helps the machine learning to learn the intricate features or all those good features from the problem. Now, when you are going to handle or analyze the data in a high dimensional space, we obviously feel a lot of issues with machine learning. So, if you are going to talk about dimension, it's a single dimension or multi-dimensional data set. Second, how many number of features. Third, whether the features are having ranking or not. Fourth, all those features are interrelated or not. Fifth, whether the model is able to properly train them or not. So this concept actually takes us into another era. That means how far the machine learning is taking into those. Now, what are the basic strength? If you're going to talk about the strength of the quantum computing, uh, actually it represent and process some higher dimensional vectors, because here most of the time you will find the product in the form of tensor. Okay, that means normally we used to have the dot product. Here we will have the vector product or tensor product. Okay, that means qubits actually represent 2 to the power n state. That means simultaneously when you are going to set number of layers in a neural network, here at the same time you have to just fix the qubits in such a way how many number of states also you are providing. The qubits are really helpful to take it into another level. That means it exploits the superposition, entanglement, as well as the interference to explore many solutions at a time. That's the beauty of quantum computing, right? Another good part what I want to discuss is some of the linear algebra operation. Like quantum computing works on basic linear algebra operation. That means you may know about the matrix multiplication, you may know about eigenvalue decomposition, and some other good, as I told you, the tensor product. So those are actually helpful, and they are the core concept of machine learning, which takes is much faster as compared to classical computing. That means when you are going to integrate or combine or hybridize machine learning along with quantum computing to make it quantum machine learning, it gives you the power of handling mathematical heavy lifting classical computers which cannot manage, and they are really responsible for data preparation as well as interpretation at the next level. Okay. So how the integration works? There are three things. The first one already I told you. You have to rely on hybrid architecture. You have to rely secondly on the quantum kernels. Third, the quantum data encoding. Participants, please do remember these concepts. These are very important for integrating any machine learning algorithm to the quantum computing. Okay. Now, most of the classical computers perform very good processing, but at the same time, they are computationally very intensive. So, we have to hybridize with quantum kernels, where the quantum computers can create some complex quantum feature space. Exactly why we need feature space? Again, to conceptualize, or in a short form, we can say to enhance few classical machine learning algorithm which exactly provide you the exponential speed up of certain problem. Because while you are going to set the qubit is not able to know what kind of problem you are going to give or what is your input, right? At the same time, irrespective of the nature of input, it gives you a very proper solution. So the quantum data encoding actually helps you to encode the quantum circuits as well as the quantum phenomena like superposition and entanglement to perform the calculations. That means classical hardware with the classical computer, when you are going to use, those are way apart, from the quantum computers with the feasibility to use the hybrid approach. Okay. One important another part I want to discuss over here, if you will see the difference among the machine learning and quantum machine learning, please see how much difference you are getting. A lot of things you are getting with all this, right? That means the left side of your screen you may find the machine learning, the right side is the quantum machine learning. Can you please see, if you are going to talk about the criteria wise differentiation, whether you are going to give the data representation to computational units or parallelism or processing speed, scalability, algorithm, or the applications. In most of the cases, you will find quantum machine learning is much more productive and helpful as compared to classical machine learning. Okay. Now, while your quantum bits, you are going to talk in quantum machine learning, you are simply talking about classical bits in the form of 0 and 1 in the machine learning, where the scalable applications you may here also find with the high dimensional problem, but in the machine learning concept, it is somewhat or some extent it is limited, right? Now, another very important concept before I will talk to quantum neural network, which is QNN. Those who knows know what is that basic neural network, like back propagation network, feed forward network, basic neural network. Now, quantum neural network, how it works and actually how much it is useful. So please correlate your early concept to the present concept. Okay. So it is very important to understand the quantum neural network in the form of different areas, and as compared to the basic neural network, it is exactly going to give you a different computation model. Now, the quantum neural network or QNN is a computation model which exactly applies to the principles of quantum mechanics, where it exactly give you the superposition, entanglement, unitary transformation, as well as to solve the machine learning problem. And can you please find it out how many parameters you are going to have it? Earlier, you are having input, output, and some layers, right? In a basic neural network structure I'm talking. So in that case, as compared to that, here you will find in the form of inputs, in you can see the basic very forward pass basic equation where u of theta and psi in and psi out. Now, the input quantum state, what is that? It is just a basic state where the parameterized quantum unitary operation is going to be performed. And what you are going to get the output? The output is again a quantum state after applying the quantum circuit, right? So everything you are going to find it out in the form of state. And if you're going to find the cost, which again we have earlier computed with a basic neural network, the cost function, and it is required sometimes in the backpropagation network as well as feed forward or MLP multi-layer perceptron, we used to compute it. Here the cost function is very easy, and if your problem is little error specific, that means most of the problem classification kind of problem, people used to consider mean squared error. No, MSC we used to normally consider. So please correlate your earlier cost function and the quantum computing or quantum neural network cost function. What is the difference? Here the C of theta, what you are going to find, it is directly dependent on the parameter theta. Now, how you are going to produce the quantum state by giving the neural network, it is exactly going to be parameterized with theta. Now, what you are going to get with O? O is what you are going to observe. That means which you are going to represent in some of the physical quantity or problem specific metric. That means if your problem is related to medical, then what are the metrics you are going to supply? If your problem is related to mechanics, accordingly the parametric, the performance metrics will change. Now, there is an observable difference among a lot of good number of states. That means if you are going to use the approach of mean squared error, you are going to have the equation on the right side of your screen, where the small components you can see. It's a very easy equation. You may find it in the form of W, What is that? It's simple, the weights of the network. Earlier also we know the weights of a simple neural network, right? What is the B? Here B represents bias. Again, we know what is bias. So what is f of xa wb? It is one of the output of the quantum neural network for the input xa. So you are going to supply the input xa, for which you are going to get the output. And what is the yz? It's the target value. Earlier also, please do remember, with the back-propagation neural network, we are having one target value. That means your output is going to be expected value minus the generated value. That means how much you are going to generate, or how your model is going to generate, minus what you are going to expect, right? The same kind of approach, it is just going to change in case of quantum neural network. And please apply any of your earlier problem which already you have solved with machine learning, right? Now let us talk about a very good concept of support vector machine. Now, we know support vector machine, but we will talk about quantum support vector machine. As I told you, my topic and inline of theme of topic is quantum machine learning, how you are going to get it. Now, before, as I assume, like everybody may little need to refresh their knowledge on support vector machine. Now, how we are going to consider a support vector machine? It's a maximum fringe hyperplane that lies in between subspaces. That means we need to exactly set the boundaries in between the feature space, right? Its structure is like that. My diagram is visible to you. Just now I forwarded it. Can you please tell?
Sir, it is clearly visible, sir. Yes,
Yeah,
sir.
okay. Thank you. So if you will go across the normal support vector machine or SVM, you please see the thick line in between two dotted lines. Now that's the basic hyperplane, and it is one of the widely acclaimed concept across the globe. Like many, if you will find support vector machine research paper in the Google Scholar, you will find many papers in almost all kind of applications, right? But there are many problems with SVM. If you will come across good papers, that means good research papers on SVM, you go to the conclusion part or the result analysis part, definitely you will find most of the research papers talks about infinite number of hyperplanes. That means how the hyperplane is not able to exactly set the boundary in between related features. So sometimes what happens, the training sample of the training data where you are going to label as either positive or negative, the maximum margin of hyperplane, it used to exactly give you the middle of the position. That means the distance in between the features to the hyperplane must be at the sorry. So the so the hyperplane you are going to keep in a the exact distance in between the features what you are going to get, but the distance has to be marginal as well as the hyperplane is maximized. Then will it work for normal any of the input? Question number one. Point two is when the data set is not trained, or you are simply inputting some of the unknown image data to SVM. In those cases, how far the sample spaces are exactly correlating to the exact hyperplane where it should. So that's the basic issue where the support vector machine starts for. Now let us talk about its just next advancement. You add quantum with that, that will become quantum support vector machine. Now, what is the beauty of QSVM? So guys, I will discuss everything, all machine learning, how you are going to integrate with quantum mechanics or quantum computing. Okay, so it's very interesting. Please see. You can see the input space on the diagram, and you can see the feature space also. How nicely the input space and the feature space and the decision boundary is exactly going to give you the kernel structure. That means the quantum support vector machine leverages the quantum kernels for the efficient data classification in dimensional feature space. Why and how? There is a feature map. Here it will help to encode the classical data into the quantum Hilbert space. Now, quantum Hilbert space exactly gives you the proper entanglement of all those features what you are trying to get closer to the hyperplane in a normal SVM. Okay, so you are going to again have some good inner product as well as some quantum states, and you are going to take some square magnitude of this inner product to give you the kernel similarity. So as I told you in the earlier slide, the quantum kernel is one of those important property which exactly helps you to come across from basic SVM to quantum SVM. Now, if you are going to differentiate, you may find these many number of advantages with quantum SVM. If you are going to talk about data encoding, it exactly gives you through the quantum circuits. Kernel computation, it is going to measure through quantum states. The computational complexity, the dimensional space, it uses directly the Hilbert space, which exactly give you higher dimension as compared to normal classical feature space. And while the training complexity you are going to consider, the quantum circuit exactly works on the depth and quantum measurements, where the linearly separable data is only possible with classical SVM. When the data becomes little nonlinear in nature or non-linearly separable, then the problem starts, as we know. Now, this is another method of machine learning, very early days method I can say, but most of the Boltzmann method, those who are co-researcher of computer science, they know this method, Boltzmann machines. Okay, so these are very helpful machines, and basically it is a unsupervised, we can say, deep learning model, because they are complex in structure as well as they are undirected. The basic Boltzmann machine concept is they are undirected, they are not directed. So what used to happen, there are two kind of nodes in Boltzmann machine. One is hidden node, one is visible node. So the hidden node used to computationally measure all the part just like visible node, but normal user cannot see it or cannot visualize it, we can say. So these machines are exactly helpful for getting the abnormalities in learning about the exact working of the system in normal condition, right? So though they are containing both the hidden layer or hidden units as well as the visible units, the performance or the complexity of the task or the complete machine is really helpful for solving many real life problems. Okay, so what do we do now? Please understand the basic Boltzmann machine. Earlier, those who know, it's a refresh to them. Those who doesn't know, please do understand. The basic main objective of any Boltzmann machine is nothing to maximize the consciousness function, the CF. CF is a very common term. The consciousness function is normally it's the state, whether it is going to change the state, either it is from 1 to 0 or from 0 to 1. That means the change in the consciousness function can exactly give you with the down equation. You can see one of the equation at the down, right? Now there are two states. If you will find the states, there are two states. One is UI, one is UJ, and the bidirectional connection among them, that means in the form of UI and UJ, you may exactly find in between the residential or residing local unit to the global unit. Now the point is how far it is exactly helpful to get the probability. Now we are able to get the probability to the network to accept the change in the state as well as by giving the normal unit with the consciousness function. That means, oh sorry, it went to next slide. So somebody typed something. Okay, so you may see the down equation here, the down term, no, the dividend term t, that's the controlling parameter. That means when it is going to decrease, the consciousness function reaches the maximum value. So you are going to consider two different kind of set of units with two connections. One is UI, one is UJ. So basically in Boltzmann machine, we used to understand UI never change its state, but that means it never change means it is either in the form of invisible unit or hidden unit. But if it does, that means if it changes its state, the information which is exactly going to reside in the local to the unit must be integrated. So that change, we are going to find it out with the probability of the network. Now, the same concept, please let us correlate with the qubit and the quantum computing. Please see now, it became QBM, that means quantum Boltzmann machine. So what I have considered a very simple tensor product, as I told you, the tensor product in between J and I, one is jth qubit I have considered, and the here one new or not new, those who knows physics little bit they can understand what is Gibbs state. Now Gibbs state is nothing but it's a basic probability of a system which gives you in a certain state of function where the states energy and the system temperature T, that means it exactly give you the probability among the system's energy as well as the system temperature. So QBM actually relies on one very good concept of physics. That concept is Ising model. Please understand what is Ising model. It's very easy to understand Ising model, and Ising model is helpful neither in QBM. It is also
But-
helpful. Hello, anybody
Sir,
talking?
sorry for interrupt. Sorry for interrupt.
Yeah,
Sir, what is the meaning of lattice, sir? In
sorry.
the second paragraph. What is the meaning of lattice, sir? Lattice means
You are
Ravindra
going
in
to.
third paragraph.
Ravindra sir, we are having the question and answer
Sorry,
session.
sir, tell me, sir.
Sir, we are having the question and answer session, sir. Okay, sir. Give me a 5 minutes.
It's okay. Actually, you are
Okay,
talking
sir.
about the
Okay,
second
okay.
paragraph,
Sorry for
right?
interrupt. Okay, sir.
No, it's okay.
Okay, sir, I can
You are
understand.
going
Okay.
to talk about lattice. Yeah, I found it. On the last
Yeah.
para you are asking. That exactly I am coming to that. Okay. So what I want to
Okay,
tell
sir.
you is the Ising model is a very important concept in this QBM, right? Like when you are going to talk about Ising model, it's a mathematical framework which gives you the magnetism of modeling a good substance of lattice of discrete spins. Now, when you are going to talk about the lattice, it exactly tell you how it is going to spin the points either in the form of either 1 or 0. That means lattice exactly means the regular arrangement of points. That means you are going to make it arrange in the form of linear combination of basic vectors. Hope you understand it. The arrangement of basic points, like how you are going to give you the lattice in the form of feature. For example, x1, b1, b stands for the bias, or you can say in the basic physics term, the discrete grid points which used to extend the infinite in all the directions. Is it clear, sir, what is called lattice?
Okay, sir. Thank you. Thank you very much, sir.
Yeah, that means we are in a basic data set, we are having number of features, right? When you are going to find the features among the feature space, how you are going to distribute the vectors. That means there we are going to talk about features. Here you are considering the vectors. Okay, and it is that lattice you can find it out in the form of kind of z1 b1 or z2 b2 or x1 b1 or x2 b2 in that form. Okay. So, sorry, it is not moving. My slide is not moving.
Yes, sir.
What happened? It is not moving. Am I running out of time? No.
No, sir. No, sir.
Okay.
No. Little bit stuck.
Yeah, it got stuck. I'm trying to move forward.
Yes, sir.
What happened? Wait.
Sir, once again,
Let me stop sharing.
yes, sir. Stop screen and again we can start this.
Okay. Yeah. Is it moving now?
Yes, sir. Moving, sir.
Okay. Let us quickly come to another important concept. Yeah, I was here, right? I'm making it full screen. Okay.
Yes, sir. Okay, sir.
Yeah. Okay. So please let us come across. Oh, sorry. Yeah. So how many of you have worked with deep learning autoencoder, right? You all people know autoencoder. It's a very good algorithm and very good model also. Like we used to have a number of solvable applications with autoencoder, and you may find this model is very helpful. Why? Because it is trained to reconstruct the inputs, and it used to leverage the hidden layer to exactly accurate the presentation of data. That means one encoding and decoding scheme is there with autoencoder. Automatically it used to give the intrinsic features of the data, right? And for your just kind reference, I have given one small equation of autoencoder. If you want to go through it, you may refer any of my research paper, because time is little limited. I'll come across. Now, please understand how we are going to get the autoencoder along with what is that? Quantum computing. That means quantum autoencoder. This concept is, you may find in the Google Scholar, you may find maximum in between 15 to 20 papers are existing in quantum autoencoder. Okay. So it's not very difficult to understand what exactly quantum autoencoder means. There are two things. Main concept of quantum autoencoder is, or basic autoencoder presentation is, how to find the loss function and how to go for the decoding function. So the decoding function, left side on your, sorry, I think right side on your screen. Okay, whatever. You may find the decoding equation at one part. You may find the loss function at another part, right? So basically, when the size of the hidden layer is less than the input what you are going to give, the autoencoder method, it exactly learns the training data. So while we are training any of the data, we need to understand whether the intrinsic units or the hidden units are linear in nature, or they actually require to ability or the ability to represent the data into the first k primary component. The fact is, most of the cases, the loss function is being calculated in case of the input data and the restructured data. That means how the data has been constructed or restructured after applying the decoding function. Okay. Now, if you will come across the quantum autoencoder, it simply have why this zoom bar is coming on my screen. It should not come. Yeah, now it is going. So while you are while you are going with quantum autoencoder, please note down a very good concept. It's called parameterized quantum circuit, PQC. Okay, so PQC completely relies on one space for the qubit, that's called Hilbert space. Hilbert space, you can see H2n, that H2 cross n means you can find it as a tensor product too. So how you are going to give the quantum circuit in the terms of vector, that you need to understand in a normal real vector space in the dimension V. So while you are going to apply the dimensional vector or the real vector in the Hilbert space, then exactly you can identify the parameterized quantum circuits, which gives you the basic structure of quantum neural network. That means you please add QNN with PQC, your quantum autoencoder is ready. If you want to see the structure, I'll show you the structure too. It's a very good concept. Yeah, this is the structure. Please you see the left hand side and right hand side of your picture. One side it is just encoder, which is again a subspace. Right hand side is a decoder, right? One and the middle structure, what exactly you saw in the autoencoder basic structure. So here the vector space is going to be find it out in the form of this autoencoder methods with sorry, it is going up. So this vector space, you are going to find it out with the proper input of encoding as well as the cross layer of hidden layer with encoding and decoding scheme of basic autoencoder, again whose output is going to decode in the form of latent vector. Okay, that's the basic concept of autoencoder as well as the quantum computing autoencoder. That means quantum computing based autoencoder. You can use this method also for many of your real life applications. Now this is now mostly widely acclaimed network, I can say, and those who works with CNN or image, they basically take CNN, right? CNN became very popular during COVID time because before to COVID, people have applied CNN in few of the applications, but during COVID, people have gone like mad with CNN for any COVID-based chest X-ray images or any image classification problem, right? And soon after, within the fraction of 2 years, again people came across with the GAN and a number of other good methods. So CNN and sorry, so CNN as well as its number of variants like ResNet or MobileNet or any other variants, they're pretty popular. And the basic concept of CNN is very easy to understand in the terms of layers, right? We used to segregate the CNN structure into convolutional layer, pooling layer, and the last, we can say the output layer, or we can say the fully connected layer, sometimes we used to call it. So basic task of any pooling layer is to downsample the result. Common pooling method used to replace the blocks of the data with their maximum and average values, where it used to helpful, or it is really taking apart with the specific features of the image, where we can take the feature in the form of dimensional matrices, and the input array is going to be supplied to the network and we will get some output. That's the basic concept of CNN. Now, have you ever imagined quantum computing also come across what with CNN? And very few people know in 2018 itself, quantum give me some water. Okay. So very few people know about this Kong. No, he is a very good researcher. If you will go through the Kong web pages, he has developed a very nice circuit structures of QCNN. Okay. What they did actually, normally what he observed, the convolution operations which are being performed on the neighboring pairs of qubits simply make them parameterized and make some unitary rotation just like regular variational circuit. That means how the convolutions are followed with pooling layer, which affects the measuring subset of qubits and using the measurement results to control the subsequent operation. So complete operation is going to be a multi-qubit operation, so that the final qubit, it is going to give you the result in the very good terms of search space. So that parameter which are learned earlier at the beginning from the matrix form of the pooling layer and all, here exactly you will find all those before the final measurement of qubit. Okay. Basic structure, please see, there is very easy structure of QCNN. The first one, as I told you, quantum convolutional layer. Earlier it was convolutional layer. Second, the quantum pooling, and everything you will find here as a space. That means vector space. So number of quantum convolution layer, how much you want to add, you can add. But normally the quantum pooling layer, it may not have that much complex structure as compared to basic complexity of normal CNN. Okay. So here there are three components. If you totally combine these three things, the input of the network, which is a quantum state, the quantum convolutional layer circuit, again it is a transitional invariant manner. It used to work with the dual qubit in a unitary matrix, and each time the UI, that means how much pair of adjacent qubit you are going to find, those you are going to take apart with the quantum layer, so that the rotational parameter will work with the quantum convolutional layer. Then what the task of quantum pooling layer? For each of the adjacent pair of qubit, one qubit is selected for the measurement. You please see, if you will go to the measurement with the pooling layer, every time one subspace is exactly connected with the next level qubit. So it actually helps to understand, and that measurement will take you to the quantum system which become smaller. That means introducing number of nonlinear factor. How? the nonlinear factor of any image when you are going to give, certainly if it is not able to produce you good accurate result, in those cases these quantum states come forward to take help of next level qubits. So this quantum convolutional neural network or QCNN is much more faster and good as compared to normal CNN. And in the beginning of my slide, I told you I will talk about one very good interesting thing. So what the title of your FDP, one paper I found in the Google Scholar related to that. If you want to go through that paper, it's a good paper. They have done a good work. But you please go to this paper. Down you can see onboard classification of underwater images using hybrid classical quantum CNN based method. They have directly used quantum CNN for taking the underwater images. Guys, please do understand all these the quantum CNN or any quantum based applications, you will find this single paper in the Google Scholar based on the topics of your FDP. Okay, directly.
Thank you, sir.
So
Thank you.
this small research I have done. Sorry, anybody is talking anything?
No, sir. No, sir. No, sir. Thank you,
Okay,
sir. Thank
okay.
you, sir. Sir, we
So-
are
so-
reaching the session time limit, sir.
Okay,
Please,
I'll
sir.
take max 5 minutes. Please give me 5 minutes. Okay?
Yes, sir. Yes, sir. Already resource person Vikram sir has been joined from IIT Tirupati.
Okay, okay. I'll just make it fit.
Thank
Just
you,
give
sir.
me 5 minutes.
Thank you, sir.
Yeah.
Thank you.
Okay.
Sir, thank you.
So these are few quantum devices. If you will go through the quantum devices, please take a snapshot, or I'll no give all this information. These are available in internet also. You can go with OpenQSAM, QSKIT, and Rigetti. All these freely available. You can directly take any good IBM based system to the next level quantum experiments. At the same time, if you will go to the TensorFlow quantum, it is very helpful for all of you. Please to understand whether it is Rigetti or IonQ or D-Wave, all these used to work with all the languages what we have covered till now, and all these. And recently I found in the MATLAB also you may find a good library according to quantum computing. Okay, so this TFQ is very helpful. Okay, so few critical insights according to me. Actually, we may take quantum computing up to the next level, but qubit as we are considering as minimum unit, so that we need to again rethink while you are designing the rotational gates and auxiliary qubits. Okay, because it is actually important for number of quantum enhanced methods. The next level task is very critical. That means we are taking it in the form of diverse domains of healthcare to image to drug discovery. But if you are going to take across the qubit, that's the minimum thing or minimum unit which is going to be used for most of the implementation. Okay. Now, what are the challenges? There are most challenges actually now issues with quantum hardware, because though IBM has come across or come forward for quantum computing devices, but still we are yet to get most reliable or most good hardware to implement any of the quantum computing algorithm. That's one of the part. Second thing is the benchmark data sets. Like for small scale data set, it's okay. But if you are going to take a high dimensional benchmark data set, for which we need some of the good noise resistant quantum hardware based devices, and those cases the classical quantum models may have some limitations. Okay, so those parts need some advancements, and as I told you, quantum computing it's still, I can say, at its early stage. We need to think little more about after some time of most of the machine learning or deep learning based applications. And I want to note here about our Indian government initiative. They have started quantum national quantum mission, and as you know, we are having 4 T hubs across India: IISc Bangalore, IIT Madras, IIT Bombay, and IIT Delhi. Okay, so those 4 T hubs have been identified to do the national quantum mission based research to basically scale up the R&D and leverage India to next level area. Okay, so this is very good option with the government of India, and they are working their target of completing this quantum mission by 2030. Okay, so that's a good thing, and the budget is very huge, more than 6,000 crore. Okay. So that's it from my side. So as you know, quantum computing is not only allow us to do some in minutes, but if you take it through lifetime of universe of the most of the advanced computer, what we use today. That means really if you are going to use quantum computing, that will take into completely next digital world. That's what I can say. I hope my session will be little more helpful to all of you to integrate or to enhance your existing machine learning based research. Thank you from my side.
Sir, thank you, sir. Thank you for your wonderful deliverables on our respected ATAL sponsored faculty development program on quantum cryptography enabled autonomous and underwater vehicles, sir. On behalf of the Department of Computer Science and Engineering in NBKRIST, we are very much thank you for spending your valuable time, sir. Thank you, sir, Nayak, sir. Thank you, sir. Another resource.
Thanks a lot. I hope
joined.
I didn't discuss with with the people. Those who are having inputs, you may please refer them my mail ID so they can refer any of their questions to my mail. I'm always
sir.
active in my mail. I will definitely mail them any of the answer, whatever they want. And
Yes.
if any help they want, definitely I'll always be ready to help. Okay.
Thank you, sir. Thank you, sir.
Yeah.
Sir.
Okay. Thank you. Thank you.
Ritika,
Yes, sir.
yeah, kindly conclude the session.
Yes, sir. I would like to extend my sincere gratitude to Dr. Janmenjoy Nayak, sir, Assistant Professor at MSCB University, Odisha. Thank you so much, sir, for sharing your valuable insights. And one more thing I would like to mention is, sir is currently looking after National Quantum Computing NQM Project 4, which is 14 crores valuable in Odisha. So this is really a great thing. We once again appreciate your presence today, sir. Thank you, sir.
Thank you. Thank you. Thanks a lot.
Sir,
Okay.
thank you, sir. Nayak, sir. Thank you very
Okay.
much, sir.
Okay.
Thank
Yeah.
you.
Have a
Thank
good FDP ahead and wish you all the best.
Sir, thank you, sir. Thank you.
Okay. Okay.
Thank you, sir. Thank you. Sir, Vikram, sir.
Hello, sir. Are you able to hear me?
Sir. Good evening, sir.
Good evening, sir.
Sorry
Are
for
you
your
able to hear me?
inconvenience. Yes, sir. You are hearing, sir. Your voice is audible.
Okay.
Sir, sorry
I
for
think
your
looks like this mic has a Bluetooth issue. Now I am using system microphone. If you are not able to hear me, message me, sir.
Yes, sir. Sure, sir. Sir, sorry
Very
for the
nice session.
inconvenience, sir. Sorry
It's
for the
okay, sir.
inconvenience.
No, it's okay, sir. That is okay, sir.
Sir. Thank you
Sometimes
for
if you are learning is okay, no problem.
Yes, sir.
Okay.
Sir, thank you for joining our session, sir. Thank you, sir.
Okay, sir.
Ritika, kindly introduce our respected Vikram Pudi, sir, from IIT Tirupati.
Yes, sir, sure. Good evening, everyone. It's my pleasure to introduce our esteemed resource person for today's event. Let us welcome Dr. Vikramkumar Pudi, sir, Assistant Professor in the Department of Electrical Engineering in IIT Tirupati. Dr. Pudi, sir, holds a PhD from the prestigious Indian Institute of Technology, Madras, one of the finest institutions in the country. Sir also completed his MTech and BTech from the most reputed colleges in the country, showcasing his strong academic foundation. Sir's academic credentials and expertise are truly impressive. Dr. Pudi sir's areas of interest include digital design, cybersecurity, and cryptography, which are crucial in today's technology-driven world. I am sure sir will share some more valuable insights and expertise with us today. We welcome you, sir.
Vikram, sir, with your permission, we are going to hand over in this session, sir.
Okay, thank you, sir. Thank you for introducing me.
Thank you, sir.
I hope everybody is able to hear me. If you are not able to hear me, please let me know.
Yes, sir. Yes, sir. Yes, sir.
Let me share my. Good evening, everyone. My name is Vikramkumar Pudi. I'm an associate professor at Department of Electrical Engineering, IIT Tirupati. Sorry, this assistant, I think.
No issues.
Okay. So today's talk is on quantum algorithms, especially Shor's and Grover's algorithm. What you can say is one of the breakthrough algorithms happened in the history is Shor's algorithm. Other one is Grover search algorithm. As you already know that when you are doing a Google search or something, usually we'll do like a searching algorithms. What is the algorithm you're using is conventional. And if you use a Grover's algorithm, even much faster it will happen. So that is what people have thought. And Shor's algorithm is a breakthrough in the cryptography. And if you are using any cryptographic algorithm, yesterday's talk we learned that if you know the secret key, we can know that one. So Shor's algorithm tells that how to get back that key kind of thing is said. So this is my introduction. And actually yesterday I have explained. So these are my credentials, like where I have did my BTech and PhD and postdoc. And as you already know that I think quantum computer, I think even D-Wave is one of the computer. I have the option to work at University of British Columbia, but I didn't. After that, I came back to NTU Singapore. And if you see that, even the quantum computer, everything is good. First, we have to, I think nanoelectronics part is not there. First, you have to understand how that our modern computer came into existence and what is the history of quantum computing and what exactly is quantum computing. Since I am not actively working on this area, I can only give brief introduction about these areas. So let me tell you, all of you know about like first whom we call father of a modern computer, Charles Babbage. And he is the first computer. He got some thought. Like, do you know why he wanted a computer? Do any of you know? I will explain that. And then the first electronic computer they used to call like ENIAC, but before that there is one more computer called ABC, and that uses like a relay kind of thing, like not a relay kind of. And then after that, when transistor is invented, that was a game changing. After followed by integrated circuit. After that, we never looked back in our history at all. Like we started getting exponential power. Like let's see. This is the history, like this is the first computer. Maybe if you go here, and the main thing is you have to understand why you wanted a calculator. So there is in 1820 and 1821 or something. If you see that there is an industrial revolution happened and people are started traveling throughout the world in the ship. The ships they wanted to make a maps, correct? But how many maps they can make? It is impossible. So they have come up with something called difference equation method or something, differential equations, where they will somehow fit all the maps into a difference equation. Then later they will try to solve it like this. So one of the person is Charles Babbage, and then he wanted like some kind of a mission. If God can give it, my work will be easy. Then he started building the first Babbage computer. You can see that how big this computer is. 10,000 pound, it's like 5,000 kilos, okay? This is the printer later they have added. This has moving parts kind of thing. And this is the difference equation formula, which you can do like a multiplication, addition, subtraction. So this is, you will input it. After that, you have to rotate it. Once you rotate it, it will do calculations. And then it will change.
నేను క్లాస్ లో ఉన్నాను తినండి నేను మీరు
Okay.
తినండి మీరు తినండి అంటే నా క్లాస్ లో ఉన్నాను మీరు తినండి
Okay. You patiently just go through this. And this is the difficult. Like you see that how beautiful it is. This is the first computer. I think all of you know about these things. So this is the one. And later what happened is there is something called vacuum tubes. People have started using that electronic like a there is some, I have deleted some of the more slides are there. Vacuum tube, it was called like a ABC computer. And here I want to tell you, previously we thought about like a decimal number system. Always we wanted to do in a decimal number system. But to get into 0 to 9 digits states are very difficult like it. So he got that idea that why you want to use always a decimal number system. And strange thing about people will get strange ideas when they are like in a crazy kind of thing. And then he suddenly got why I want to use base 10, why can't use base 2 number system. Then he created a first computer. This is called ABC computer. And this is the one, but actually what happened is he never made any money or something. He just invented and then he retired and he quietly went or something kind of thing. And later that ENIAC came and they claimed that this is the first electronic computer. That time, if you see, there are many lawyers used to visit this person like ABC computer. He is the one first used like electronic, but the name came to ENIAC. And later, you see here that ENIAC computer is very, very huge, like 2 lakh man hours and then $500,000. You can do compound interest of 8% or 6%. It was very, very huge money. Like, so they spent so much money to do simple calculations, not like very, very big calculation, very, very simple calculations. You know, can any of you tell me what is the operating frequency of this computer? So 5,000 additions, 5,000 additions cycles second. Per second, it used to do like a 5,000 additions. It means the frequency is 5 kilohertz. So it is used to operate at 5 kilohertz. Maybe it can be expanded to 100 kilohertz. That is what that 5. Remember that 5 kilohertz and binary we are using. Later, that transistor invented this person. Actually, what he did is he has his own time or something. Then he invented a transistor. Like he has a not in the job separately. He has invented, and this was a breakthrough in the history of the world. Like. And then it is created a switch using the transistor. We are able to create all the circuits. There is one more guy. What he thought? Okay, I want to make a circuit. I have to bring a resistor and then capacitor, inductor. Why can't I make everything with the silicon material and a single wafer or something, which used to make like a transistor? Then that idea has been got like a breakthrough. Then they created an integrated circuit. Same, like this is the best idea. They got it. And there are two people like Jack Hilbert, two are in different industries. They got same idea. They invented, okay. On the same wafer or something, you can make all the circuits. And after that, we never look back. Like there is something called integrated circuit came in 1960. And after that, 1990 or something, Intel 4004 or something. They got a microprocessor. You see here 1971 Intel, I think 1971 Intel microprocessor. It operates 1,000 transistor, 1 megahertz operation. So all these things are working on a binary kind of thing, integrated circuit. Like. But there is one more thought. Like for example, what happened is the space, like for example, for our needs are increasing, like day by day, these transistors are not enough. Currently, we are at like a 2 to 3 gigahertz operation. Maybe we are in 100 billion transistors in the same size of IP or something. It is happening like. And that what happened is the person whom we call like father of nanoelectronics or quantum computing, whom Richard Feynman, what in a lecture, why we are looking in the, like there is a lot of like below the electron, like an atom or something, we have a lot of area, why can't use that area kind of thing. These are all like a timelines of quantum computing. So the first is 1900 is like, maybe you can say that 100 year or 120 years old is like a quantum. 1900 that guy got idea and you understand that there are no computers, nothing like it. And 1970 like birth of quantum information theory happened. And you can see that so very slowly they're progressing or something, quantum cryptography or something. 1984 there is one person, his protocol he has proposed. And after that, Peter Shor, like he created an algorithm. You have to understand he is one of the person who did his thesis on the quantum, and then he even attended Richard Feynman's lectures also. Like he has Richard Feynman somewhat incomplete in the quantum, so they try to work it like a very different. It's not easy. Like you see, even 2000 also not many people have been bothered about this. Even 2007 there's something called they want to make like a quantum or something. And you see 2013 onwards, there is actually, you know why? Lot of big companies, government, they are spending a lot of money on quantum. So it started improving like anything. Now you see that quantum, one of the main reasons why people are going to quantum, Shor's algorithm. All our cryptography, everything we can break if you know Shor's algorithm you can implement in a quantum computing. So what is a quantum computing? So quantum computing, basically you know about logic gate, logic 1 or 0. But quantum usually uses the spin of an electron. So the spin of an electron, it can be in any direction. So okay. So we define it is an upward means there is a bit called a Q bit we call it as it is a 0, it can be 1, it can be in a diagonal, any state. It is the basically it can be in any state, like whether it can be in 1 or 0, both the state it can be there. So to represent any Q bit as we don't represent like a binary like logic 1 or 0, we'll represent alpha Q bit 0 plus beta. It's kind of a mathematical or physics way of representing Q bit because you want to compute some operations. So you want to control a Q bit. And quantum computing, if you see here, it's called a Bloch spin. For example, electron spin is what in the quantum computing we want to control it. Correct?
Sir,
Electron can be. Hello?
hello.
Hello? Are you able to hear me? Hello?
Yes, sir. Yes, sir. Yes, sir. Sorry for the inconvenience, sir. Some of the participants has been disturbing.
Okay, so this is the expression which will give you the where exact. This is called Bloch three-dimensional sphere or something. For example, somewhere my electron here is there, the spin. It is the equation which will give you the spin of the electron. We can. So this is the Bloch sphere. Usually want to control, we will create some logic gates or something. So this is the, for example, y direction. This is what x direction means. We can represent like this. So usually basis state, you can take z as a basis state, you can take x. If you take z as a basis state, we will represent x in x basis in terms of like this. Okay. Similarly, y also will represent like this imaginary y or something we'll get. So this is called a basic representation of a qubit. Like it means it's called electronic spin. Imagine you know how many electrons in your atom contains. Are you so that many number of we are able to control it, we will do like a lot of wonders though. So there are many ways of fabricating this. One is called quantum dot based ones, where they will trap the ions and trapped ions. I think this is what IBM is using. And superconducting, like they will use copper pairs to do the quantum qubits. And hello. And
Yes,
you
sir.
know that
Sir,
what is the difference? One simple explanation I will give you.
Hello, sir. Sorry for
One simple
inconvenience.
explanation I will give you. What is a classical computer? Let's say in the classical computing or something, we are sending some ball or something or some electron. Either it can be in this place or this can be either of this one place only. Like if you keep it like you can only observe here or here only one. This is a classical computer. But in a quantum computer, you take some kind of electron or whatever, you pass it like this kind of slit or something. It is some kind of, it can be in any of these places. For example, it can be here, it can be here, it can be here. But what we will measure is probability. For example, you take this one. What is the probability of electron being here? Okay. Probability of being. So always quantum will measure probabilities, not with the normal like logic, like how we will measure voltage and current. This is the one of the important aspect of quantum computing. So there is something called quantum entanglement. I think giving. So this is the one of the way method people are using for key establishment. So there are two qubits they will take and they will prepare a Bell state. And then let's assume that in Earth I am in these two qubits. Let's go to far away from the Earth. For example, these two has to be should be in the same state and same kind of maybe quantum, some polarized laser polarized or something we are communicating. And if you change this qubit, this will also change according to that. And if somebody third person will come try to know what it is A and B, this key, whatever it is established, it will get destroyed. This is the entanglement principle. Similarly, if A changes B, but if somebody measures, this will destroy that entanglement. We know that somebody trying to hack it, that will lose the information. So now this quantum key establishment protocols are what people are designing using lasers, many methods like from the satellite to establishing from the ground earth for key communication people are doing. And also one more thing, everybody thinking that quantum logic gates are like basically same as like our conventional logic gates, but they are very completely different. They are in the form of matrix kind of thing or something. For example, you want to create any quantum logic gate, it should be a complex conjugate. Complex conjugate, why we need? We will get ensure real eigenvalues, means there exists some real solution. Similarly, they are unitary. You have to become, it should get eigen, ensure the probability, you are able to do. These two properties you are able to observe, it is very good. And you can see that classical bit 0 or 1, you can use transistor. Qubit usually always will measure in terms of probabilities. We don't get actual values or something. Okay. This is the difference. And we have like a NAND gate and all these things. Similar manner, in a quantum, we have like a different gates. There's something called Pauli X gate, Pauli Z gate, Hadamard gate, and there is one called controlled NOT gate, control NOT gate kind of thing. These things we will have always. And if you see these gates, this introduction, this is not. You can go through the basics. This Hadamard gate is the one of the interesting gate. Usually, Hadamard gate, what it will do is, it will give you equal probability. For example, I have one state 0 or 1 or something. If I'm in a 0 state, if you measure that probability is 1, correct? If you measure it. If the 1 state, it will give probability 0. But if you apply Hadamard state, it will always give you that equal probability. Whether you measure in 0 state or 1 state, it will give you equal probabilities. So this is the very, very interesting. I think you should remember. And know about this one, 1 minus 1 by square root of this. So there is one more thing. This is called controlled NOT gate or something. Usually used for XOR operation. And remember, quantum gates are like a reversible gates. Reversible gate in the sense, for example, I gave you X, I gave you X or Y. I know what is, I can get back what is Y. This is called reversibility. So all the quantum gates are reversible gates. And that's why always you will have like equal number, how many number of inputs I will have, that many number of outputs. If they are not reversible, they are not a quantum gates. This is the one more like a Toffoli gate. If I give you A, B and C, X or A, B, I can find out by using this C gate, C also. So these are all like some of the gates. And remember, this is the one, I think there is one more. This phase gate is the very, very interesting, and Hadamard gate. These two gates are like very, very interesting gates, even this phase gates. So you know about this is the quantum full ladder. You see this is the conventional full ladder. And how do you design a quantum full ladder is, you will take whatever gates. For example, this is control, this Toffoli gate, this is control NOT gate. By using this, and remember here, all of you know, my output are two here. Here my inputs are 3. Actually, but here you can see that there are 4 states are there, 4 outputs are there. That is the where difference comes from the quantum and as well as conventional. This kind of some dummy kind of state. And quantum full ladder, and if you want to give input, you will do initialization on these bits, and you will get if you measure it sum or something, you will get back a original values. And you know, quantum computer, you want to represent multiple qubits. This also like alpha, beta. Okay. So like this, you can represent, and you know that there is a, okay. For example, I have pack of cards or something, correct? In the pack of cards, usually, let's say I want to find, it has been randomly stored in some place or something. For example, each K has been assigned some 9 number or something. B has been, this one has been assigned like Queen has some 27 number or something. Randomly, I have kept it in some kind of, you want to search it. For example, I want to find a hearts of 7 or something. In general, how many iterations classical algorithm will take? Usually it takes like a normally n iterations in the worst case. Some cases it will take n by 2 number of iterations, maybe searching algorithms. So what he tells is, if you use Grover quantum or something, for example, quantum state or something, it is if you can predict these things, usually it takes like n by 2 or something. But I can take like very less number of times in a square root of n number of iterations. I can find out where exactly that chord is there. That is the Grover search algorithm. So to do this one, first you have to prepare something called, for example, let's have them that heart, spade, clubs, and diamond. I have stored like some quantum states or something, but we don't tell which one it is. And you have to find out that this diamond. For example, here diamond I have assigned to 1 0 state or something kind of thing. So first thing, we have to prepare a oracle. Oracle in the sense you will prepare something kind of an identity kind of thing. You assume that spades are shared here or something. This is called oracle. You will create identity matrix. Then we will apply for in oracle gate. And whichever state you want to make it, that one will make like a negative kind of thing. And you will apply Hadamard gate. When you apply Hadamard gate, everything will become like a equal problem. Then once you apply, again you will do diffusion kind of thing. It will become like, for example, everything will become, if you do like a diffusion, whatever value you want to set, it will become like a negative kind of thing. And this is like intermediate stage. Again, we'll do Hadamard, and then we'll do one more time like Pauli gate or something. At the end, what will happen is, if my state actually is in 1 0 state, I will get probability here 100%. If this is not in the state, I will get in other state some kind of a equal some different probabilities or something like that. So if you see Grover search algorithm, you can use a quantum chi-skit as IBM. Oracle is the one which is a whichever you want to prepare. This preparing this function is there. After that, you have to use a reflection function. Finally, you have to measure it. When you measure it, whichever, for example, here I want to find W kind of thing. It will reflection will do negative, and then when I measure it, this will become highlight, like if that is present in the state also. This is called Grover search algorithm. And for example, I have qubits. For example, I wanted to find if these qubits are like state 110 or something. This is called the oracle preparation. First, you have to prepare an oracle, and then you have to do the diffusion layer. Again, you have to repeat it like 2 times this one. So at the end, what will happen? If I measure, let's say my input of 3 qubits, I apply like 0, 0, 0, the probability very less. But if I apply this Grover search algorithm to measure, if my input is 110, this probability of measuring of this algorithm is very, very high kind of. So I can know this is my input 110. And there's some other case we'll get high probabilities also, some other input copy. So this is how usually we do Grover search. Since I'm not working in this, I don't have any programming. This is the usual search algorithm. And there is one more thing. Yesterday I had discussed about key exchange or something. Digital signature algorithms, which I discussed digital signature algorithm is in general, we wanted to approve any document or any letter or something, we send to somebody to sign it like a paper or something. The bank person or somebody will verify the signature is not correct or wrong or somebody who is processing that document. In case of a digital signature, how do you know means this is like, for example, we don't know, like it is very difficult process to do signing in the manual, like 1 million. For example, you download an Aadhaar card or something, correct? How do you know that is the original Aadhaar card? You give to somewhere to process it or something. How do that guy know that is your Aadhaar card or somebody Aadhaar card or something? So digital signature means it will take some message or something. It will compute the hash algorithm. And then using this private key, it will generate a signature. The signature is what usually sorry, here we'll do, for example, we'll take a message and then we'll get a message plus signature and transmit to other side. For example, that guy want to verify, he will get the signature and then he will verify it. Like this is called digital signature. And how this will work is, this works based on the RSA algorithm. So RSA algorithm works on two principles. One is like a n equal to p multiplication with q. P is a prime number, q is a prime number. And when you have these two, now you will take very large prime numbers, you multiply them. P and Q, you multiply with them. And the n it will come. N is actually like some kind of a public key, part of a public key. As well as there is this one more thing you will find out, like a Q of n or something. This Q of n is like very easy. Euler total, you can find it very easy. And this GCD of this one will become like a n. N you have to find, it will become like public key kind of thing. You can choose, there is something called n, e, which is like a GCD of e, comma, this compute pi n should be one. There should be co-prime, that will become a public key, but private key I will compute a different manner. So what I will do is, I will take some plain text, message e or something, m power e, I will take this public key, I will compute a ciphertext. So this ciphertext is what used for, I will send to other side. This other side in the sense, key exchange, yesterday we have discussed. So what that guy will do, he has his private key D, C power D mod n he will do, he will get back his original message. Yeah, this is the RSA algorithm. All of you remember, one common operation here is m power e, C power D, mod n. Okay, here mod n is C m power e. So this is doing like a G power D mod n kind of thing. So this is the one. First is like a, how do you choose like P and Q? After that, how do you compute this thing and thing? Again, you have to compute a Euler total, and then I have to generate private and public. So this is one of the example. I will give you more detailed example later. But this RSA algorithm, when they have introduced, it is like very common. SSL, TSL, email encryption, digital certificates, all the places is what RSA we are using. And if you see RSA, the key sizes means this public key and private key sizes. We have public key and private key sizes, correct? This 1024 bit, usually this size actually are able to attack, like security level is very low. 2048 bits means medium kind of thing. And 4096, currently we are using like 4096. If quantum computers or Shor's algorithm come, it can break it, but the current security and conventional it is way. You can see some more example. RSA 1024 is almost equal to, we have discussed about AES, correct? AES, 80-bit, how much it is the security, similar security it will give. RSA 4096 is same security level as AES, is like 140-bit security. So means it will take 2 power 140-bit, but it is a maximum security, but our quantum computers can break easily. So how quantum computers breaks? Before that, I will give you some RSA example. You see, you take some two prime numbers, P and Q, you multiply it, and you will get it. And then you can kill it, Euler total, and then you will get something. So this one, we have to choose E such that the GCD of pi of n and then 7 should be kind of a 1 or some co-prime. And after that, you will calculate a public key and private key. Here you see the private key and public key. And then I have message. For example, 88 I want to transmit to other side. I will take 88 power E kind of thing. Here is like a part of a public key. Here is 7. You can see that 887 mod 187. Actually, we have to compute. For computing, there are different algorithms usually they will use. This don't bother about it. So I will get ciphertext 11. This 11 is what I will transmit to other side. So I have a private key here, 23, 11 power 23 mod 187 I will do. And then I can compute it. So this 11, anyway, we are transmitting like an insecure channel. But if I find out 23, I can get back my secret key kind of. So this is the record message 88. That's how usually will get it. Some more example you can see. But what exactly drawback about this algorithm is, let me give you some brief about Fourier transform. Usually, what is a Fourier transform? For example, I have a time-based signal. It doesn't matter how many times it repeats or something. When I convert it to 1 Hz of the frequency domain, it will tell you that the frequency of the signal is 1 Hz. So it means every 1 Hz my signal is repeating. And how do you construct a Fourier transform? Fourier transform itself is like this is the Fourier transform formula. But if you go and look into like a 2-point Fourier transform or something, usually 2-point Fourier transform we can compute using Hadamard gate as well as some phase e power I theta. This is called phase shifting gate, which is available in the quantum. In the quantum, we can even do the how much we want to rotate a spin of a qubit electron, so that actually if you club Hadamard gate, let's assume that this is so Hadamard gate followed by the phase gate. Hadamard gate followed by the phase gate. Actually, it gives a quantum Fourier transform. In general, quantum Fourier usually maybe for us we feel very difficulty. Fourier transform implementation is very easy in the quantum computer. So this is the basis. Like what happened in Shor in 1994 or something. He has come up with this Shor's algorithm, prime factorization. You know that RSA algorithm uses a two polynomial P, and if you know that P and Q, we can get back our secret key. So you use this concept to get back this prime factorization. You would anyway, I know N. I want to find out what are the P and Q. That is what this prime factorization. If I know that is very. So how did he come? Let's assume that you can take some sequence of numbers like it are in the 2 powers. Correct, all of them are 2 power or something like that. And if you do mod 15, you can observe some strange sequence that 2481. Again, it is repeating 2481. So after 4 or something, for example, okay, here R is like here 2 power 4. Onwards, again the sequence is repeating. Here R is like a 4. And mod 21 you take like. And 1, 2, 3, 4, 5, 6. R equal to 6. After the 6 sequence, again it started repeating. If I know that this R, when it is repeated, I can find out like mod 21. This is what gave idea. So what exactly it will do is, these sequences are periodic. If I know the R, I can find out which of this one. So this is the one. So we have to find out the order of A means smallest positive R such that A power R equal to mod 1 or something, which you have to find entire thing. Once you found these things, you will apply like Euler theorem and all these things. You will get back to get. So you will R must, and also R will divide P minus 1, Q minus 1 also. That is also one more condition which he has proved. So if I know that R, I know that this will divide this one in this one, and A power this one equals to this one, and definitely I can get back my R. P and Q values. So eventually, for example, if I know, I can find out P minus 1 Q minus 1 because R will divide this ones. So it's and P and Q are like prime numbers. It's easy to find. So you can find P and Q. That's it. So this is some proof. This is some proof. So you don't need. So this is the Shor's algorithm. This looks like very simple. First, you take like N, which is like you want to find output P or Q. That's if you find out P, I can find out Q. Anyway, N is a public key. I know that one. I have to find a P. First, what I will do is I have to find out A. I have to choose. Anyway, A also they will give as a. So I will have to choose like some of the A. And then from that, I will use order function. I will find out R. If R is even, again, I will do like this one. And GCD of whatever X and N, it will give you the P. Okay. So if P is greater than 2, looks like very 3-4 steps. Once we do in a quantum computer comes, whatever we are doing like 1090, 4096 or something, it only requires 1000 qubits to break our RSA algorithms. How to find this R? That is the main question. This is where quantum magic happens. Usually, R can be very large. So what people have done is they will apply quantum Fourier transform period of this. They will find out like whatever a power I or something. They will apply here. You see that the sequence wherever it is repeating kind of thing in the time domain. You can see that Fourier transform kind of thing. Correct. Fourier transform. You apply wherever that is periodic, it will repeat kind of thing. And then you will do frequency analysis of this. Wherever the spikes are there, that is where it will give you the R. So it is how usually quantum Fourier transform, key ingredient, quantum Fourier transform. As I told you, quantum Fourier transform, you will use like a basis for this, and then you will create this kind of a modular function, and we will give it to them. Wherever the periodicity comes, this phase of this signal will go up kind of thing. This is how usually we'll end up getting a Shor's algorithm. This is how we will map. You can use like IBM quantum Q-skit or something like this. So this is the how we'll map all these things. That's all. That is the one about these things. Since I have prepared very less on this, if you have any doubts, you can ask me now. If you want, I can go. I have some more slides on the quantum dot cellular meter, but this is not relevant to me. I want to complete it by 8:25, so I have done somewhat first. Thank you, everyone. You have any doubts, you can explain. You can tell me. Hello, are you able to hear me?
Hello, sir.
Hello, sir.
Sir, can you please show me the slide? It is related to superposition and entanglement.
Where it is? Oh, okay.
I have one doubt, sir. If you don't mind, please show me. This one, sir? No, sir. Please go back, sir.
Oh, you mean this slide?
I think a superposition and entanglement slide is there.
This one?
No, sir. It is also understood. Can you please go back, sir? Previous one. Wait, sir. Wait.
This one.
No, sir. I think it is, sir.
This one, no?
No, go back, sir. No, sir. All these are
Ravindra sir,
understood.
if you are having a problem, just you can give the slide number, sir. Sir will be recognized very
I don't,
easily.
sir, I think in between the range, in between 15 to 20, sir, I think. I think the slide number is, the range of the slide is 15 to 20. Yes, sir, please. It is, sir, slowly.
This one, no?
I think it is 24, sir. 24.
Oh, I will go
Sir.
through, sir. This one?
Oh, I think 24, slide number 24, sir.
Okay, this is block sphere, sir. This is a block sphere.
Sir, triple one, sir, physical.
Physical implementation of
sir.
sir. Yes, sir.
Okay,
physical
okay.
implementation of qubits. Yes, sir. Yeah,
Yes,
yes,
sir.
sir.
Tell
Then
us.
what is the meaning of Cooper pair, sir?
Sir, this is a superconducting, sir. Actually, what will you... Superconducting pairs, sir. Actually, what will happen, these pairs usually will have zero resistance, correct? So this is all about controlling the spin of electrons, sir, actually. How do you control this? Usually fabrication, I didn't go through much details, actually, this thing. People are using that the superconducting ones where they can get actually this Cooper pairs means maybe, the resistance is very, very zero kind of thing. That is what called Cooper pairs.
Okay, sir. How the
Which one,
Cooper
sir?
pairs will forms in quantum computing, sir?
The Cooper,
How the
actually,
Cooper pairs will form in quantum computing?
see, I didn't work on the fabrication parts of this one. Actually, I'm only I'm only working the circuit point of view only. Maybe I will send you some papers related to this, sir, later. Okay, I will send to.
Okay, sir. Thank you.
Okay, I will send to that
Sir,
Chandrakant,
thank you,
sir.
sir.
You can take. Okay.
Okay, sir. Okay, sir.
And all of you, there is a one more thing. If you are really interested how to fabricate or something, there is a University of New South Wales. They work on this quantum computing. They are the one of the first universities to fabricate a quantum computer, quantum qubits. So they have this how to fabricate a quantum. All the papers they have listed out. University of New South Wales, sir.
Yeah. Thank you, sir. Okay, sir. Okay.
And they are Andrew Jurak, like I have known that faculty also. He is also. Any other doubts, sir?
Respected participants, if you are having any queries, sir will be awaiting in our respected question and answer session.
Sir, can I ask one more doubt, sir?
Yeah.
Please, sir. Please, sir.
Is it possible to implement quantum computing in wireless sensor networks in terms of gates, sir?
Actually, sir, you wanted actually quantum computing is not possible to do in a classical computer, sir. But what you can do is there is a quantum Q-skit, sir. IBM Q-skit. They will give some free of maybe I can screen. Quantum Q-skit IBM. Actually, these what basically you write a program or something, sir, like Python or something. You can just I think like this you write some Python code or something. That should be connected to their IBM cloud computer where that can run in their quantum computer. It will give back our data, sir. There are some
Okay,
recently.
sir. Thank you, sir. Thank you.
Sir, there is one more. You know that.
Yes.
It's called emulation of qubits, designed by the NVIDIA recently. They have released a library. If you really want to do emulation, how these qubits are working, rather than going for this IBM, for free of cost, NVIDIA is giving the emulation of qubits, means quantum emulation of quantum computer. Output of that algorithm is same as this Q-skit. You will get, sir. Okay, sir. Hello.
Okay, sir. Thank you, sir. Thank you very much.
No. Any other questions?
Respected participants, sir will be awaiting in question and answer session.
This actually like if somebody wanted to buy free is an open plan, very limited. Like for example, you wanted to pay something, you have to go $96 per minute. You see, quantum computers are very expensive. $96 per minute. Okay. That's why it's not easy to like. There is a one more academic tool. Let me show you. Think. Okay. Quantum Inspire. Delft, I think Netherlands once. I think this is free. I think, but that is also will have. Yes, quantum. Okay, program your quantum algorithms. This is what I used my students to use it, like introduction to quick guide. You can use this one. This is a free of cost. You can even go for quantum full order, which I have taken. Okay, so this is the algorithm. It will run their own quantum computer. But they are also very busy. But this is a free of cost, at least. Like if you wait for some more time, it will run it. So usually to build a quantum computer, they have spent 10,000 crores or something. That's why they're charging like 10 And there's many algorithms, many companies they are wanted to use it. So they will do charging like this. Okay.
It is more expensive, sir.
This is actually will increase even more, sir, after some time.
Yes, sir.
Because to fabricate a single qubit, even if you provide 1,000 crores, it is not possible, sir.
Sir.
Yeah, to that equipment itself will cost like a University of New South Wales, that Australian university, $2 billion they took to just to fabricate qubit like that. 10
Australian.
years before I'm talking.
Okay.
10 years before I'm talking.
Sir.
Okay, sir.
Is there
Okay,
any question and answers? Just
by the way, I'm just learning. Maybe if you call me next year or something, I can give you better about all this algorithm. Even I can tell you how to break a RSA algorithm also. By programming, I can tell you. Okay.
Sir. Sir, we are planning to organize one more faculty development program, sir, as a physical manner. Sir, kindly accept our request. We are keenly looking for your physical participation from the Department of CSE and NBKRIST, sir. Kindly accept our request from our end. Give me your free time. That time we can plan. We will discuss our honorable respected HOD, sir, and we will plan according to that, sir.
Okay, sir. Thank you, sir. Okay. I'm happy to visit NBKR. All of you know or not, actually, I wanted to join at NBKR that time, but my rank is like a little bit higher. Second counseling I could have got, but I got triple E. Like I wanted to go for ECA, so I have chosen Narayan Engineering College.
Sir.
I'm happy to come there, sir. And second counseling, after joining second counseling, I didn't apply.
Sir.
But for us in the Nellore surrounding area, NBKR is the best college at that time. Sir.
Yes, sir. Yes, sir. Yes, sir.
Sir, can I ask one more question, sir?
Please, sir. Please, sir.
Sir, actually, what type of problems are best suited for quantum approximate optimization algorithm, sir?
Quantum approximate?
Optimization algorithm.
Sir, usually, let me tell you one thing. For example, this adder is the correct n-bit adder, which will take more time to, for example, you take some classical multiplication. I implemented in quantum, I implemented conventional thing. Which one do you think will take more time? Quantum will take more time. Certain algorithms are not suitable for the quantum computing. Certain thing, for example, you asked about optimization, correct? Usually optimization algorithms are very suitable to solve using the quantum computer. Similarly, search algorithm. Quantum cryptography, crypto analysis, people are using a quantum algorithm. It's only suitable for, sir, you are asking about optimization. Sir, you have idea about optimization?
Yes, sir.
Yes. Actually, optimization in the conventional time, it takes like a exponential time, correct? In the quantum computer, it will take linear time.
Okay.
But you have to design all the circuits like this, sir. It is a little bit challenging, but it is excellent if you are able to do some optimization problem. It's very good, sir.
Okay, sir. Thank you, sir.
Any other thing, sir? And students, I suggest you to learn in the quantum. Maybe in the future, this quantum will become like one of the, like people will ask about, do you know quantum language or not? Like once these quantum bits are cheap to fabricate it. Okay. Okay, sir. Can I leave, sir?
Yeah, sir. Please.
Thank you, sir.
1 minute, sir. 1 minute, sir. Sir, thanking you for accepting our request for participating in our ATAL sponsored faculty development program by the Department of CSE in NBKRIST, sir. We are very much grateful for your participation, sir. Ma, Ritika?
Yes, sir.
Ma.
Yes, sir.
Yes,
I would like to extend my heartfelt gratitude to Dr. Vikramkumar Pudi, sir, for sharing his valuable insights and expertise with us today. Your presence has enriched our understanding on cybersecurity, cryptography, and digital design, sir. I also thank our organizers, participants, and everyone involved in making this session a success today. Your enthusiasm and engagement are truly appreciated. Thank you all for joining today's session. Thank you, sir, for your presence once again.
Thank you. Thank you. So thank you for inviting me.
Thank you, sir, Vikram, sir. Thank you very
Thanks,
much, sir.
thanks.
Thank you very much, sir.